We are going to start now lecture 9 of chapter 7 class 11th mathematics, permutation and combination. In this lecture we will study some formulas related to arrangements in groups. So the first formula we have over here, it is, we are saying the number of ways in which n different things can be arranged into r different groups. And the first case we are discussing over here, that the blank groups, they may be allowed or they may not be allowed. So if the blank groups are allowed, suppose we have n different things we are talking about. These are the things 1, 2, 3, 4, 5, say 6 things are there. We are talking about the first case when we have 1, 2, 3, 4, 5 and 6 items are there. And we are saying that we have to arrange them in, we are saying the value of n we have it is 6. Suppose the value of r we have it is 3. That is, these things are to be arranged into 3 groups. And we are talking about the case the blank groups are admissible. This is the first case we are saying. So if we are talking about that we have to arrange them in 3 groups, I am talking about I have to arrange these in 3 groups. First group may be empty, second may contain 1, 2, 3, 4 and next will contain 5 and 6. So we are saying that if we are arranging them in groups, so I have to mark some points over here. If I mark one point over here and another point over here, so automatically these things, these are divided in 3 groups, first group, second group, third group. So we are saying that if we have to divide them in 3 groups, it means we have to mark 2 points. We have to mark 2 points. So if we are saying that we have to divide them in r groups, it means we have to mark r minus 1 points. We have to mark these many points. So if we mark these points and we have total 6 objects. So what we are now talking about, we have in total, if we find the sum of all these, we have total 8 places at which we have to arrange these 2 points. It means if we are talking about, we have total n objects and there are r minus 1 places we want to arrange. So we are saying, we are talking about that we have n plus r minus 1 places and we have to choose r minus 1 places out of these. And these n objects we are talking over here, these n objects, these 6 objects, they themselves can be arranged in 6 factorial ways. That is, these things, these can be arranged in n factorial ways. So the answer we obtain, it is n plus r minus 1 factorial divided by r minus 1 factorial into n plus r minus 1 minus r plus 1 factorial into n factorial. These values gets cancelled and this n factorial gets cancelled with n factorial, and the answer we are left with is n plus r minus 1 factorial divided by r minus 1 factorial. And on solving this, the answer we obtain in this case, it is r into r plus 1 into r plus 2 so on up to r plus n minus 1. So we are saying that if n different objects, n different things are to be arranged in r different groups with the condition that the blank groups are admissible, then the total number of cases we will have, it is, this can be done in r into r plus 1 into r plus 2 so on up to r plus n minus 1 ways. Second case, we are when the empty groups, they are not allowed. So in this case we are saying the total, suppose I am again talking about, we have 6 objects, 1, 2, 3, 4, 5 and 6 objects. We want to arrange them in say 3 groups. So now what we want to do is, we want to mark 2 points over here corresponding to these 3 groups. We want to mark 2 points over here, and the number of places to mark these points, we cannot mark this point over here because it will correspond to the empty group. We are saying we cannot mark it over here. So the number of positions we have, it is 1, 2, 3, 4 and 5. So if we have n objects, we are saying the number of positions to mark these points, it is n minus 1, and the number of points we have over here, it is r minus 1. So we are saying the total number of ways we will have, it is arranging these points, it is n minus 1 c r minus 1, and these n points can be arranged in n factorial ways in themselves. So these are the total number of required ways, that is n minus 1 c r minus 1 into n factorial. So based upon this, the first question we have is, in how many ways 5 different balls can be arranged into 3 different boxes? So the value, so that no box remains empty. So we are talking about the case, we are saying we have 5 different balls, 1, 2, 3, 4 and 5. We have to arrange them in 3 different boxes. We have 3 different boxes. It means we have to mark 2 points over here. So these 2 points, these can be marked in, we are saying 5 minus 1 c 2 minus 1 into 4 factorial, 5 factorial, n factorial it is. So the answer we obtain, it is 4c2 into 5 factorial, that is equal to 720. So this is by applying the direct formula. Otherwise, how we can see this result is, we are saying the first case we are talking about, it is that box we have, first box, second box and third box. In these boxes, we are saying the number of balls that can be arranged, it can be 1, 1 and 3, because no box should remain empty, or the number of balls that can be arranged is 1 ball in this, 2 balls in this, 2 in this. So what we obtain from this is that if we look at this condition, we are saying we have 3 objects and 2 of them, they are same. If we look at this condition, the number of ways of arranging this is 3 objects, 2 of which are same. Now these balls, these can be arranged in, we are saying these balls can be arranged in 5 factorial ways. So either this thing can happen or this thing can happen. So we have to add both these values. So the answer we will have over here, it is 120 into 3 plus 120 into 3. So the final answer again we obtain, it is 720. Next is the number of ways in which n different things can be distributed into r different groups. Now the term distributed is over there. In the previous case, we were talking about the arrangement. Now we are talking about the distribution of n different things into r different groups. So suppose we have r groups, they are G1, G2, G3, so on up to Gr. And we are talking about the first case in which the blank groups, they are allowed. So total number of these we are talking about, we are saying we have r groups. So in how many ways these can be arranged? We are saying it is r raised to the power n. We are talking about blank groups are allowed. Then r group, these n different things, these can be arranged in these r groups in r raised to the power n ways. We are talking about the blank are allowed. Second case, we are saying the number of cases in which the group G1, we are saying group G1 is blank. We are talking about the number of cases in which group G1 is blank. It will be r minus 1 raised to the power n. That is, we are saying that G1 is blank and rest, the remaining groups we have, it is r minus 1 and n objects are to be arranged. So we are saying from this what we obtain is the number of cases in which G1 is not blank. It is r raised to the power n minus r minus 1 raised to the power n. Now out of these groups we are talking about in which G1 is blank, we are saying the number of groups in which G2 is blank, that will be r minus 1 raised to the power n minus r minus 2 raised to the power n. So the number of number of ways in which G1 and G2 are not blank. That will be r raised to the power n minus this value we are saying r minus 1 raised to the power n minus r minus 1 raised to the power n plus r minus 2 raised to the power n. So this gives us r raised to the power n minus 2 times r minus 1 raised to the power n plus r minus 2 raised to the power n. Now from these groups we are saying in which G1 and G2 are not blank, the next case we are saying it is that G3 is blank. So we have the number of cases that will be given by this. So the number in which G1, G2, G3 are not blank is given by this formula. We are trying to generalize this result. On generalizing, if we continue this process and generalize this result, we are saying the number of distribution in which no one of X assigned groups is blank. So it is given by this formula. We are talking about that no one of the X assigned group is blank. It is given by this formula. And in this result, if we substitute X is equal to R, the final answer we obtain it is in this form. So these are the total number of ways we are talking in this case. So this will be more clear to you with our next examples. Now the next question we have is, in how many ways 5 different balls can be distributed into 3 boxes so that no box remains empty. So we are saying that 5 balls can be distributed in 3 boxes. The total number of ways we have it is 3 raised to the power 5, that is equal to 243 ways. We are saying the total number of ways we have it is 243 ways. Now when we are talking about these 243 ways, it also includes the empty boxes, but it is being given that no box remains empty. So the first case we are talking over here, out of these all cases, we are removing the case when one box is empty. So we have 3 boxes. Out of these 3 boxes, we are choosing one box, and if one of these boxes is empty, it means that we are left with this 3 minus 1 boxes in which 5 objects, 5 balls are to be placed. So the answer we obtain in this case, it is 3C1, it is 3, and it is 2 raised to the power 5. So it is 3 into 32, that is equal to 96. So we are saying that there are total 96 ways in which one of them will be empty. Now we are talking about the case when 2 of them are empty. So out of these cases we have to remove that. So we are saying if 2 of them are empty, we have to choose out of these 3 boxes, we are choosing that 2 boxes are to be empty, and the number of cases we are left now, it is 3 minus 2 raised to the power 5, because in one box all the 5 balls are to be placed. Now 2 are empty. So the answer we obtain in this case, that is equal to 3. The third case we will have when none of the three they are empty. So we are saying that 3C3, and we are having over here 3 minus 3 raised to the power 5. So the answer we obtain it is 0. Now look at these conditions carefully. We are saying the total number of ways we have it is 243 ways. This includes the case that one box is empty. This includes the case that 2 boxes are empty. This includes the case that all the 3 boxes they are empty. This includes all these cases. Now from this case, we are subtracting the value when one box is empty. When one of these boxes is empty, it means this includes the case that 2 boxes are empty. Now what we are left over here is that 2 boxes are empty or 3 boxes are empty, because when we are saying that one box is empty, this will also include the case that 2 boxes they are empty. This also includes the case that all 3 boxes they are empty. It means that we have to add the number of terms. We have to add the number of terms in which these two boxes we are saying they are empty. Then we have to subtract the number of terms in which we are saying 3 boxes they are empty. On solving this, the final answer we obtain it is equal to 150. So this is basically the formula we are applying over here. It is this value we are saying it is 3 raised to the power 5 minus 3c1, 3 minus 1 raised to the power 5, then 3c2, 3 minus 2 raised to the power 5, and minus 3c3, 3 minus 3 raised to the power 5, and answer you will obtain it is 150. Another way of solving this is, this value we are saying this is basically the coefficient of x raised to the power 5 in 5 factorial e raised to the power x minus 1 raised to the power 3. If I open this term, I will get it is 5 factorial into e raised to the power 3x minus 3 e raised to the power 2x plus 3 e raised to the power x minus 1. We are talking about the coefficient of x raised to the power 5 in this term. So if we look at the coefficient of x raised to the power 5, it is 5 factorial 3 raised to the power 5 by 5 factorial minus 3 into 2 raised to the power 5 by 5 factorial plus 3 into 1 by 5 factorial. On solving these terms, the final answer we obtain again it is 150. So you can directly apply this formula or you can use this result to find the answer in this case. Next, another way to look at this answer is, we are saying that each box must contains at least one balls, because it is being given that none of the boxes is to be empty. So we have these two cases, that box 1, 2, 3 they can have 1, 1 and 3 balls, box 1, 2, 3 they can have 1, 2, 2 and balls. So in this first system we are saying the number of options in which this can be done, it is 5C1, that is out of 5 balls we are choosing 1, then out of 4 balls we are choosing 1, then out of 3 balls we are choosing 3 balls, and further we are talking about the case 1, 1 and 3. Further we are saying that in how many ways this 1, 1 and 3 can happen. It can happen in 3 factorial by 2 factorial. 2 factorial is these two, these are same. So we are saying the total number of ways we will have it is this much. In the second case, in this second case we are saying the total number of options we will have, it is 5C1 into 4C2 into, when these 3 balls are being distributed we are left with these 2 balls, 2C2, and again this distribution can be done in 3 factorial by 2 factorial ways. So the total number of options we have it is sum of these two values. Now 3 factorial by 2 factorial means we are saying it is 3, 3 factorial by 2 factorial we are saying it is 3, and these values if we calculate, it is 5C1, it is 5 into 4 into 1 into 3, and this value it is 5 into 6 into 1 into 3. So the answer we obtain it is 60 plus 90. So the total value we will obtain it is 150. So these are the 150 cases we are talking over here. Next is, in how many ways can 5 books be tied up in 3 bundles? So clearly none of these books should be, none of these bundles should be empty. So we are saying that the number of ways we will have it is 3 raised to the power 5 minus, out of these 3 bundles we are choosing 1 and we are left with these 2 books, then it is out of these 3 we are choosing 2, we are left with this 1 book. Now we are talking about the bundles, and these bundles we are saying that these are indistinguishable. So what we are saying that there are 3 factorial different bundles that we can form, and these cases these correspond to these 3 factorial different bundles. But we are saying that if these 3 bundles these are indistinguishable, it means we have to divide this value with 3 factorial because these bundles are indistinguishable. So the answer we obtain in this case it is 150 by 6, that is equal to 25. Next is, if number of elements in A is 5, number of elements in B is 3, find the number of onto mappings from A to B. So the definition of onto mapping, we are saying we have two sets A and B, and we have 5 elements in this set A, and we have 3 elements in this set B. So we are talking about the elements of this set B, that each of this element should have at least one pre-image. We are saying it should have at least one pre-image. None of the elements over here it is unmapped. So this is equivalent to saying that the number of ways in which 5 different balls, pre-images we are saying, can be distributed to 3 different boxes. We are saying these are the 5 different balls we have, and these are to be distributed among 3 different boxes, and no box remains empty. And we know that the answer in this case, that will be 3 raised to the power 5 minus 3c1, 3 minus 1 raised to the power 5 plus 3c2, 3 minus 2 raised to the power 5. This kind of result we have already done in our first chapter related to sets. Number of cases we have over here, it is, we are saying 243 minus 96 plus 3 is equal to 150. So finding the onto map is just the similar problem. We are saying that we have 5 different balls. These are the 5 different balls which are to be kept into 3 different groups, and none of the groups remains empty. Next is the number of ways in which n identical things can be distributed into r different groups. It is, these results we have already seen, that when we are talking about distributed, the number of ways we are saying it is n plus r minus 1 c r minus 1. When we are talking about the number of arrangements, we have multiplied this with n factorial. Now we are talking about distribution. So we are talking about, these are the cases when the blank groups are allowed, and the number of cases when blank groups are not allowed. When blank groups are not allowed, it is n minus 1 c r minus 1. So this word distributed is important over here. So these results we have already seen in our previous slides. So if we are talking about the case if blank groups are allowed, we have seen that the result we have it is this, that n plus r minus 1 c r minus 1. So another way of solving this is, we are saying it is the number of distributions of n identical things into r groups. It is a coefficient of x raised to the power n. This thing we are talking about, that if we want to find this, it is equivalent to finding the coefficient of x raised to the power n in the expansion of 1 plus x square raised to the power r, or in x into x square, x cube, so on raised to the power r, accordingly as blank groups are allowed or they are not allowed. So these kind of results, these will be more clear to you when we will move to our next chapter of binomial theorem. So at this moment you can just give a reading to these results, that these values we are saying, these are just the coefficients of the binomial and multinomial expansions that we will study over there. So based upon this, the question we have is, in how many ways 5 identical balls can be distributed into 3 different boxes so that no box remains empty? So we are saying the answer we have it is 5 minus 1 c3 minus 1, because the word distributed is over there. So answer we obtain it is 4c2, that is equal to 6. Next is 4 boys picked up 30 mangoes. In how many ways can they divide them if all mangoes be identical? So this is just the case. We are saying that a boy may be there who will not receive any of the mangoes. So it means that we are talking about the case of distributing 30 objects in 4 groups, and empty group is allowed. We are talking about this case, and the answer in this case we know it is 34 minus 1 C4 minus 1, that is equal to 33 C3, that is equal to 33 into 32 into 31 divided by 3 into 2. On solving this, we will obtain the total number of options we have. It is 5, 4, 5, 6. These are the total number of options we have in this case. Next is find the positive number of solutions of equation x plus y plus z plus w is equal to 20 under the following conditions. First is 0 value of x, y, z, w are included. So it is being given that the numbers, the positive number of solutions we are saying, it means that x, y, z and w we are saying. First case is 0 values are to be included. We are saying that these values should be greater than equal to 0. It means how many different values of x are possible? 20 values of x are possible. 20 values of y, 20 values of z and 20 values of w are possible. So we are saying that solving this, that 0 value of x, y, z, w are included. Solving this is equivalent to the question that we are talking about, that 4 groups are there. 4 groups means we are talking about x, y, z and w groups are there. And how many values we have? It is 20 values we have. So the number of ways of doing so when the empty groups are allowed, it is 24 minus 1 C4 minus 1. So answer we obtain it is 23 C3. The answer we have it is 1771. So we are saying the total number of options we have it is 1771. Second case we are talking about is 0 values are excluded. 0 values are excluded. Now again look at this equation, it is x plus y plus z plus w is equal to 20. Now the condition we have over here is that x is greater than equal to 1, y is greater than equal to 1, z is greater than equal to 1 and w is greater than equal to 1. So on solving these values, we are writing it is x minus 1 is greater than equal to 0, y minus 1 is greater than equal to 0, z minus 1 is greater than equal to 0, w minus 1 is greater than equal to 0. And we make the following substitutions. X1 is equal to x minus 1. So we get x is equal to x1 plus 1, y is equal to y1 plus 1. If we substitute it in the given equation, if we substitute these values in the given equation, we will obtain the question in the form that we are talking about, that x1 plus y1 plus z1 plus w1 is equal to 16. And now the condition we have is that x1, y1, z1 and w1 is greater than equal to 0. So we are saying that this is equivalent to solving that 16 objects are to be distributed in 4 groups and the empty groups they are allowed. We are saying the empty groups are allowed. So the answer we will have it is 16 plus 4 minus 1 C. 4 minus 1, answer we get it is 19 C3. And this value comes out to be 969. Or another way of solving this question, it is, we are saying that how many total values we have, it is 20. How many groups we want to form, it is 4. And empty groups are not, we are saying empty groups are not allowed. So the answer we will have it is 19 C3. This is the same value we are obtaining in this case. So you can solve this question in either of these ways. Either you can consider that the empty groups are allowed and you have to transform it into this new system, or what you have to do is, you are talking about the case that empty groups are not allowed and you directly use this formula and you obtain it is 19 C3. Next is, how many integral solutions are there to x plus y plus z plus r is equal to 29. It is being given that x is greater than equal to 1, y is greater than 1, z is greater than equal to 3 and t is greater than equal to 0. So we can write these equations we are talking about. This first we are writing Suppose x1 is equal to, we are saying x minus 1 and it is greater than equal to 0. Second we are talking about, it is y minus 1, we are writing y1 is equal to y minus 1 is greater than equal to, it is not greater than equal to, it is greater than 0. Then we have z1 is equal to z minus 3, it is greater than equal to 0, and t is greater than equal to 0. Now look at this term over here, we are saying y minus 1 is greater than 0. So in place of y minus 1, if I write y minus 2, and I will get over here it is greater than equal to sign. So if we make the substitution to this equation, we are getting from this that x is equal to x1 plus 1. So we are getting it is x1 plus 1 plus y1 plus 2 plus z1 plus 3 plus t is equal to 0. This last value we are saying this is not r, this is t. So to solve this system, what we obtain from this is, this is not equal to 0, this is equal to 29. We are saying this value it is 29. So what we obtain from this is that x1 plus y1 plus z1 plus t, that is equal to 23. This value we will have 3 plus 3 6, on this side it is 23. So if we solve this value, we have total 23, value of n it is 23, and the value of r we have it is 4, number of groups we have 4, and the condition we have it is greater than equal to. So the answer we obtain it is 23 plus 4 minus 1, C4 minus 1, and on solving this the answer you will obtain it is 26 C3, that is equal to 2600. So these are the total number of ways we have in this case. Or another way to solve this problem it is, we have transformed the equation in this form, we have used these transformations, and we are obtaining the equations in this form, that x1 is greater than equal to 1, y1 is greater than equal to 1, z1 is greater than equal to 1, t1 is greater than equal to 1, and equation we have is x1 plus y1 plus z1 plus t1 is equal to 27. So the total number of ways in this case we are saying, in this particular case we are saying the value of n we have it is 27, value of r we have it is 4, and we are talking about the case that empty groups are not allowed, because we are saying that the values we have now it is greater than equal to 1 in all these cases. So the answer we obtain it is 26C3, it is same the answer we have obtained in our previous case. So it is up to you that how you want to solve these kind of problems. Next is how many integral solutions are there to the system. It is x1 plus x2 plus x3 plus x4 plus x5 is equal to 20, and it is given that x1 plus x2 is equal to 15 and xk, all these values these are greater than equal to 0. So if we talk about this system first, we are talking about the system x1 plus x2 is equal to 15. We are saying we have total 15 plus 2 minus 1 c, 2 minus 1, that is equal to 16, c1 is equal to 16 solutions in this case. And if we substitute this value x1 plus x2 is equal to 15, we substitute in this equation, we will get x3 plus x4 plus x5, that is equal to 5. So the total number of solutions we will have it is 5 plus 3 minus 1 c3 minus 1. The answer comes out to be 7c2, that is equal to 21 solutions in this case. So we are saying, these are the steps we are saying, that x1 and x2 can have 16 values, then x3, x4, x5 can have 21 values. So by fundamental principle of multiplication, the total number of solutions we will have it is 16 into 21, that is equal to 336 solutions. So these are the total number of solutions we have in this case. Now next we have is find the number of non-negative integral solutions of 3x plus y plus z is equal to 24. So we are saying, suppose the value of x we are saying it is equal to k, then this equation can be written in the form y plus z is equal to 24 minus 3k. So the solutions we require over here, we are saying it is non-negative integral solutions. So clearly we have the value of y and z, it is greater than equal to 0. So we will have the condition that 24 is greater than equal to 24 minus 3k is greater than equal to 0. So this gives us, if we solve this equation, we will get it is 0 is less than equal to 3, k is less than equal to 24. So this gives us 0 is less than equal to k is less than equal to 8. So the possible values of k we have it is from 0 to 8. So to solve the remaining part, we are talking about this value over here. Y plus z is equal to 24 minus 3k, where k is lying between 0 and 8. We are saying the total number of solutions of this equation, that will be 24 minus 3k plus 2 minus 1, c2 minus 1. The number of the value of n we have it is 24 minus 3k. The value of r we have it is 2. On solving this, we will get it is 25 minus 3k c1, that is equal to 25 minus 3k. So we are saying that the total number of integral solution of this equation, it is 25 minus 3k. And the value of k can vary from 0 to 8. It means we are saying when the value of k is 0, the number of solutions we will have it is 25 minus 3 into 0. When k is 1, the number of solutions we will have it is 25 minus 3 into 1. Likewise, when k is equal to 8, the number of solutions we will have 25 minus 3 into 8. So by fundamental principle of addition, the total number of solutions we have it is sigma k is equal to 0 to 8, 25 minus 3k. This is equal to 25 sigma 1. We are saying k is equal to 0 to 8 minus 3 times sigma k, k is equal to 0 to 8. This gives us 25 into how many total value, how many times this 1 is being added. We are saying 1 plus 1, so on up to 9 times. So we are saying the value we will have over here it is 9 minus 3 into the value of k, sigma k, when k is varying from 0 to 8, the answer we will have it is 9 into 8 by 2. So the answer we will get over here it is 225 minus 108, that is equal to 117. So these are the total number of cases we have in this particular question. Next is the number of ways in which n identical things can be distributed into R groups so that no group contains less than L things and more than M things. It is given by the coefficient of x raised to the power n minus L into R in the expansion of the term 1 minus x raised to the power m minus L plus 1 raised to the power R into 1 minus x raised to the power minus R. So from our previous result, we know that distributing n identical things to be distributed in R groups, so that the things they lie between, the number of groups they lie between L and R, it is given by the coefficient of the term x raised to the power n in the expansion of x raised to the power L. We are saying it should have more than L groups, plus x raised to the power L plus 1, so on up to plus x raised to the power m whole raised to the power R. We are saying these are R is the number of groups and these are the terms we are interested over here. We are saying that no group contains less than L things and more than M things. So we are saying this is equivalent to, this term we are saying this is equivalent to the coefficient of x raised to the power n. From all these terms, if we take x raised to the power L common, we will get x raised to the power L into R into 1 plus x square so on up to x raised to the power m minus L raised to the power R. So we are saying this is the coefficient of x raised to the power n minus LR in the expansion of 1 plus x so on up to plus x raised to the power m minus L whole raised to the power R. This term, if we look at, this is just like the GP we are saying. So we can write this is equivalent to, the sum of this GP will be 1 into 1 minus x raised to the power m minus L plus 1 divided by 1 minus x, and this power we have R over here, and we are writing this term in this way. So we are saying it is the coefficient of x raised to the power n minus LR in the expansion of this term, this expression we are talking here. So the question based upon this we have, in how many ways can 3 persons each throwing a single die once make a sum of 15? So if we are talking about the throwing of a dice, we are saying the minimum number we have, it is 1, and the maximum number we can have on the dice, it is 6. The number of persons we have, it is equal to 3. The number of groups we want to form, it is 3, and n we have, that is equal to 15. So applying this formula, we obtain that we are interested in the coefficient of x raised to the power 15 minus 1 plus 3 in, that is equal to x raised to the power 12 in the expansion of 1 minus x raised to the power 6, the minimum value we are saying, into 1 minus x raised to the power minus 3. We have power 3 over here, the value of R that we have. So when we solve this term, when we solve this value, we are saying this is coefficient of x raised to the power 12 in the expansion of 1 minus x raised to the power 6, we are saying whole raised to the power 3 is there, and this is the expansion we have, and second term we are saying it is 1 minus x raised to the power minus 3. We are having the terms in this form. This is a binomial, infinite binomial expansion we are talking about. So from these terms we will obtain the final answer in the form that the coefficient we have over here, it is 10. How we are solving this, this will be more clear to you when we will move on to our next chapter of binomial theorem. So right now I am not discussing these calculations in detail. We will see that how these calculations are made in that particular chapter. So right now we are just restricting ourselves to up to this case, that we are talking about the coefficient of this term in the expansion of this polynomial, you can say. We are not writing polynomial because it is power minus 3 over here. So we are just saying the expansion of this expression. Next we have is, how many ways are there in which an examiner can assign 30 marks? The total marks we have, total marks is 30. Total questions is 8. And he has to give at least 2 marks to each question. So minimum marks he can assign, it is 2. So suppose he assigns 2 marks to 7 questions. So if he has assigned 2 marks to 7 questions, then the total marks he has assigned, it is 14. So the next question, the last question will have, the total marks is 30. So he has to assign 30 minus 14 is equal to 16 marks. We are saying that he has to assign 16 marks. So what our problem becomes now is that the total number of questions, that is equal to 8. The minimum marks to be assigned, that is equal to 2. The maximum marks to be assigned, that is equal to 16. And the total marks we have, that is equal to 30. The total marks we have, that is equal to 30. And we want to find how many such arrangements are possible. So we are saying that this minimum value 2, we are saying this is the value of L we have, and this is the value of M we have, So the formula we obtain from this is that the required number of ways, it is coefficient of x raised to the power 30 minus 2 into 8 in expansion of, in expansion of 1 minus x raised to the power 16 plus 16 minus 2 plus 1 raised to the power 8 into 1 minus x raised to the power minus 8. So we are saying this is equivalent to the coefficient of x raised to the power 14 in the expansion of 1 minus x raised to the power 15 raised to the power 8 into 1 minus x raised to the power minus 8. Now by using the binomial theorem, we will have the value of 1 minus x raised to the power minus 8 will be given by this expansion, and the coefficient of x raised to the power 14 from this value we will obtain, it is 21c7. So we are saying that there are total 21c7 ways of doing this distribution. Next is, if a group has n things in which p are identical, then the number of ways of selecting r things from a group, it is given by this formula, that it is sum of r is equal to 0 to r n minus p cr if r is less than equal to p, and it is sum of this value when r is greater than equal to p. So based upon this, we have this problem. We are saying a bag contains 23 balls in which 7 are identical. Find the number of ways of selecting 12 balls from the bag. So over here we are saying the total number of balls, it is 23. The balls which are identical, it is 7. And how many balls we have to select, it is equal to 12. So clearly we have the case that r is greater than p. We are talking about the case r is greater than p. So the answer we will have, it is sum of r is equal to r minus p, 5 up to r, it is 12, and the value we have over here, it is n minus p. N minus p means we are saying it is 16c r. So we are talking about the term over here. We will get the answer as 16c5 plus 16c6 plus so on up to 16c12. We know that ncr plus ncr minus 1, that is equal to n plus 1 cr. So if we add these first two terms, the answer we will obtain, that is equal to 17c6. Next term we will have, it is 16c. At the next two terms, it is 17c8. Next we will have, it is 17c10, and next we will have, it is 17c12. By adding two terms, we will get the answers in this form. Now if we look at this term over here, we are saying 17c10, that is equal to 17c7, and 17c12, this is equivalent to 17c5. So now collecting these two terms, we are talking about these two terms, it is 17c5 plus 17c6 plus 17c7 plus 17c8. So on adding these two terms, the answer for this term we will have, it is 18c6 plus 18c8. So this is the final answer we obtain in this case. These are the total number of ways we have over